In the last lecture, we have seen that the class of Liebig measurable sets is very big, and in particular it is closed under taking complements, taking countable unions, and taking countable intersections. So in this lecture we will look at some equivalent criteria for Liebig measurability. We have given one definition of Liebig measurability, and we will see that there are plenty of other equivalent criteria that one can write for the definition of Liebig measurable sets. So I'll state this as a theorem. Let E be an arbitrary subset of Rd, be an arbitrary set. Then the following are equivalent. So the first is E is Liebig measurable. Of course, we want to give equivalent conditions for Liebig measurability. So the first one is basically just the definition of Liebig measurability. This is there exists given epsilon greater than 0, there exists. So let me fix given any epsilon greater than 0, there exists an open set U containing E such that the outer measure of the complement set complement U minus E is less than or equal to epsilon. The second one is it can be termed as almost open criteria, which says that given epsilon greater than 0, there exists an open set U. Now E may not necessarily be contained in U, but nevertheless we have that rather than the set difference, we will take the symmetric difference. U symmetric difference E is less than or equal to epsilon. So here the difference between one is that E may not be a subset of U. The third is approximation by closed sets, inner approximation by closed sets. So this criteria says that given epsilon greater than 0, there exists a closed set F contained in E. This is an inner approximation, so F is contained inside E such that the outer measure of E minus F is less than or equal to epsilon. The fourth condition is similar to the almost open condition. This is the almost closed condition, which says that given epsilon greater than 0, there exists a closed set F. Now F need not be contained inside E. That's the only difference between this case and the third case, such that outer measure of F symmetric difference E is less than or equal to epsilon. And the fifth one, this is almost measurable condition. This says that given epsilon greater than 0, there exists a measurable set E epsilon such that the outer measure of let me write it u epsilon symmetric difference with E is less than or equal to epsilon. So here all these sets, this set and this closed set in the last condition, all of them depend on epsilon. So let me put an epsilon everywhere. This is u epsilon, u epsilon, u epsilon, f epsilon. So these are 5 equivalent conditions. So we have listed 5 equivalent conditions for the if you want to test whether some given set is Liebig measurable or not. So let's try to show this. So few of these implications, we will start with one, and we will see that few of these implications are quite trivial. For example, 1 implies 2 is trivial. This is trivial because if E is if you have an open set u epsilon containing E, then that will also satisfy this condition here, because if it satisfies this condition, then this condition is, the second condition is trivial. Similarly, 3 implies 4 is trivial. So 3 implies 4, this is also trivial. And 4 implies 5 is also trivial, because if you can find a closed set, then a closed set is a measurable set. So fifth one is automatically satisfied if 4 is satisfied. So 1 implies 2 is trivial. So let me note down these things, these remarks. So 1 implies 2 is trivial. Then we have 3 implies 4 is trivial. 3 implies 4 implies 5. These are also trivial. So one just has to show that 2 implies 3 and 5 implies 1. Then we will be done. So let's try to show whether 2 implies 3. So let epsilon greater than 0 be given. Now note that 1 implies 3 is quite easy to show, because if we have an open set U containing E such that m star U minus E is less than or equal to epsilon, then so this implies that E is Liebig measurable. E is Liebig measurable. Then this also implies that E complement is Liebig measurable. This we have shown before, that if E is Liebig measurable, then so is E complement. So then there exists an open set V containing E complement such that m star of V minus E complement is less than or equal to epsilon. Now we have, if we want to prove 3, which is to give a closed subset of E such that outer measure of E minus F is less than or equal to epsilon, then we can take F to be the complement of this set V. Let F be V complement. Then the outer measure of E minus F is, this is equal to M star E intersection F complement, which is equal to M star E intersection V complement, but this is nothing but E intersection V, but we can also write it as V intersection E complement, and this is nothing but M star of V minus E complement, and this is less than or equal to epsilon. So this, from the Liebig measurability of the complement, we deduce a set F lying inside E. So F is lying inside E and F is closed, such that M star of E minus F is less than or equal to epsilon. So 1 implies 3 is easy. So let's show that 2 implies 1, and then that would imply that in turn that 2 implies 3. So we have broken up this into 2. The first one is 1 implies 3. This is easy, and we will also prove that 2 implies 1, and so this will imply that 2 implies 3. So let's try to show that 2 implies 1, which means that we are given, so this is 2 implies 1, given epsilon greater than 0, there exists an open set U such that the outer measure of U symmetric difference with E is less than or equal to epsilon. Now U may not contain E as a subset, so we have to find an open set U prime that contains E in this case, such that the outer measure of U prime minus E is less than or equal to epsilon. So to produce such an open set U prime, we will use what we already know from this inequality. So let me take epsilon by 4 here, and you will see why I am taking epsilon by 4. So note that M star of U minus E is less than or equal to M star of U symmetric difference E, which is less than or equal to epsilon by 4, because since the symmetric difference is the union of U minus E and E minus U. Similarly, M star of E minus U is also less than or equal to epsilon by 4. So now we can use the outer regularity property of the Liebig outer measure. So this implies that there exists an open set V1 that contains U minus E such that M star of V1 is less than or equal to M star of U minus E plus, I am going to take epsilon by 8 here, so that this is bounded above by epsilon by 4 plus epsilon by 8, and this is equal to 3 epsilon by 8. Similarly, there exists an open set V2 containing E minus U such that the outer measure of V2 is less than or equal to 3 epsilon by 8. Now take U prime to be the union V1 union V2 union U. So it's a union of 3 open sets, so it's open. U prime is open, and U prime contains E as well. U prime contains E. So check this. Now I want to show that M star of U prime minus E, I am claiming that M star of U prime minus E is less than or equal to epsilon. So let's see why. So M star of U prime minus E, this is less than or equal to M star of V1 union V2 union U minus epsilon minus E, and this is less than or equal to M star of V1 minus E plus M star of V2 minus E plus M star of U minus E. But the first two terms are bounded above by M star of V1 plus M star of V2, and then you have M star of U minus E, and so this is less than or equal to 3 epsilon by 8 plus 3 epsilon by 8 plus epsilon by 4, which is equal to epsilon. So we have shown that U prime is an open set that contains E, and the outer measure of U prime minus E is bounded above by epsilon. So this shows that part 2 implies part 1. So going back to the beginning of the proof, we had two things that we needed to show. The first one was that 2 implies 3, so this we did, and now we have to show that 5 implies 1. So recall that 5 is the almost measurable condition, which says that given epsilon greater than 0, there exists a measurable set U epsilon such that the symmetric difference of U epsilon with E is less than or equal to epsilon, and then we have to produce an open set that contains E such that the outer measure of that open set minus E is less than or equal to epsilon. So this would be 5 implies 1. So let's try to show that 5 implies 1. For this purpose, we will have to define a couple of new notions. So let me define the notions of limit superior and limit inferior of sets in RD. So let n equal to 1 to infinity be a sequence of subsets of RD. They may not be subsets of RD. This is a very general notion, but since we are only dealing with subset of RD for the moment, so I have taken them to be subsets of RD. Then we define the limit superior as n goes to infinity of an. This is by definition the intersection n equal to 1 to infinity of the union m greater than or equal to n, so m from n to infinity a m, and similarly the limit inferior liminf of a n as n goes to infinity. This is the union n equal to 1 to infinity, and then we take the intersection of m equal to n to infinity a m. So to gain an idea of what these lim sups and liminf describe, the following lemma is quite useful. It says that the liminf of a n's as n goes to infinity, this set can be described as the set of all x in Rd such that x belongs to all but finitely many a n's. So all but finitely many, meaning that there may be finitely many a n's, say n1, n2 and nk, for which x does not belong to those sets, but it belongs to all the other sets. Similarly, the lim sup of a n as n goes to infinity, this is the set of all points such that x belongs to infinitely many an's. So the difference between the two is that x, for the second one, x may not belong to all but finitely many. For example, e.g. for x in lim sup of n, we may have that x belongs to a n for all n even, and x does not belong to a n for all n odd. So in this case, there are infinitely many sets a n such that x does not belong to those sets. So this x does not belong to the liminf, but it belongs to the lim sup. But in any case, we have that liminf of a n is a subset of lim sup of n. So this is a corollary of the lemma, that because this set is defined, if we take this definition as the set of all x which belongs to all but finitely many, and the right hand side is belongs to infinitely many. So of course, if x belongs to all but finitely many n's, then it belongs to infinitely many n's, but the vice versa is, the converse is not true, as we see in this example. So in this way, we have a more tangible definition, or more practical definition of what lim sup and liminf actually describe. Now we will use these two sets to prove our implication from 5 to 1.